Hey everybody, welcome to the stream. Today we're gonna do a lot of physics questions. They're listed at the bottom of the page. So let's see if everybody's in the stream. So chapter 3, so this is kind of based on the homework, FYI, but chapter 3, page 45, question 37, 39, 40, 54, 61, 75, and 85, and then chapter 10, question 39, 41, 50, and 52. So, let's start. Okay, hold on, let me reposition. Okay, I can now see the live chat, so if you have any questions, you can ask me in the live chat. Time for the first question, which is 37. Time to get a different color size pen. 37. Okay. 37. So, 37 goes like this. An electron in an old-fashioned television picture tube is accelerated at a constant rate from 2e5 meters per second to 1e7. Ooh, that's a tenth the speed of light. Well, 30th the speed of light. In a 12 millimeter long electron gun, what's the acceleration of the electron? What time interval is needed for the electron to travel the length of the gun? What am I looking for here? I'm looking for a pen. Okay, that one's over there. Okay. So, this is pretty fun. The deal is you're going to learn some of this next term. But the deal is that in the old days, the television sets had these things called electron guns in them. Now they're LCDs. So now the way they work is light is produced in some of them are in LCDs. LCDs have screens behind them, so it's like a white light shines through, and then they filter out different colors so that a little patch is blue, a little patch is red. Some of them are LEDs where there are pixels emitting it, but in the old days, the way it worked like this: you'd have a really hot wire. It'd be heated with electricity, so you have a current running through it, and really hot wires, they discovered, shoot off little particles, little electrons in this case. And what you do is you'd also make a thing that has an electric field. So these ones are negatively charged. Over here is positively charged. And so charges would feel, no wait, it goes this way. No, I did it wrong. Shoot. So the electric field goes that way, and these charges will feel a force pushing them through the thing and accelerating them. And then you'd have a stream of charges moving through, a steady stream of charges. You would have another device that could aim the charges, bend their direction depending on which one you wanted, and then the charges would hit a fluorescent screen and cause a little bit of the glass screen that everybody would look at to light up. And so it's kind of funny, if you go see an old TV, these are they're called cathode ray tubes. They predated the naming of the electron because these were called cathode rays. They travel in straight lines. And so your cathode ray tube would send a beam at the screen that would move down in this pattern. And it would snake its way down the screen in a fraction of the second, and then it would restart at the top. And this way, you could shoot pixels in places that you wanted to be bright, and you could not shoot parts where you don't want to be bright. And thus, you could make it so that an image appeared on the screen. And you would do it over and over and over, several times a second, and your image would change depending on what. And that's essentially how television works. It's a wonderful system. So you don't need to know any of that for this particular question. In this question, all they're telling you is that there's an electron gun. That was the thing that shot the thing with the filament at the start. So let's try it. The deal here is that your electron starts from rest, and then, oh, maybe it doesn't start from rest. It starts from moving, and then it ends up moving quite quickly. So it's initially moving at 57. It's initially moving at 2.0 E5 meters per second, and in the end, it's moving at 1.0 E7 meters per second, and the distance here between the two is 0.012 meters. So the question is, what's the acceleration? Of course, the acceleration is going to be to the right, so fine. And how much time is required? And the trick to doing these questions is to just start out. We'll say t is equal to 0 there. No, t is equal to 0 there, and we'll call its initial position x is equal to 0. And we'll say moving to the right is increasing. And then we'll just go from there. So your initial position is going to be 0. Your initial time is 0. Your initial velocity is 2.0 E5 meters per second. And your acceleration is unknown. So you put these together in your constant acceleration equations, and you get, no, geez, no, I don't want this. Go away. 2.0 E5 times time plus a over 2t squared, and v is equal to 2.05 E. Wait, no, hold on. 2.0 E5 plus a t. And so this is interesting. This is something you don't see very often in class. There's a bunch of things you don't know. You don't know the position, but you also don't know t, you also don't know a. There are a lot of things you don't know in this system. So what we're going to do is there's going to be another set of information given. So they're going to give us information about the motion at a certain time, or they're going to give us information about the motion in a certain position, and we have to fill in the blanks. Because essentially, what you want in the very least when you're doing these problems is you want 2 equations and 2 unknowns, essentially. So, how do we do that? Well, we know that at t is equal to, I don't know, I'll call it t end. The position is at 0.012 meters, and we know that at that time the velocity is 1.0 E7 meters. So let's fill that in. So 0.012 is equal to 2.05 2E5t plus a over 2t squared, and this one is 1.0 E7 2.0 E5 plus a t. I guess I can call it t end. So there's 2 things we don't know here. We don't know what a is, and we don't know what t end is, but we can solve for these algebraically. How do you do that? You solve and substitute. I guess I better do it, huh? Yeah, this is a 2-star problem, incidentally. So I'll move this over to this side, and that gives you 1E7 minus 2E5 is equal to 9.8 E6 is equal to A divided by, you know what, let's solve for A first. And then we substitute this in for these guys, and you get 1.0, nope, be good, just once, 0.012 is is equal to 2.0 E5 times 9.8 E6 over A plus A over 2 9.6 E 9.8 E6 divided by A all squared. Let me do some algebra here. No, not algebra. Arithmetic. 2E5. Just getting the calculator out. 0.8E6. So this is, oof, well, it's not surprising. 6E15 over A plus squared divided by 2. This is 4.8 E13 divided by A. So combine them together, 1.96 E15. You get 2E15 divided by A, and then you rearrange and you get 2E15 divided by 0.012. You get that number, which is bonkers. So how much time does it take? Let's see. Let's plug this number into here. 1.0 E7 is equal to 2.0 E5 plus 1.673 E17. I would have guessed that you would have had to take the square root somewhere in there. It's bananas. T and I'm just going to take out my calculator and calculate this value. So it's 1E7 minus 2E5 divided by 1.673 E17. 5.85 meters per second. Does that make sense? One question you might always ask is, does that make sense? Because, wait, hold on. I forgot the E minus 11. So, yeah, does that make sense? How do we answer if that makes sense? Well, one way to do this is we know the range of velocities the thing had. So if it was traveling at the max velocity, one E7 and the distance is 0.012, then the amount of time to go that distance is 0.012 divided by 1E7. Oh, come on. 0.012 divided by 1.0 E7. It'll be 1.2 e to the 7, 8, 9. 10. I think I made a mistake in there somewhere. That's 0.012 divided by when I calculate how much time it took if it was going its maximum speed, I end up with a number that's bigger than if it was accelerating. So there must be something wrong in there. I'm tired of this question. Let's move on. So there's probably just an algebra mistake somewhere in there. I'm feeling pretty absent-minded today. So somewhere in the middle here, there's a mistake. The first person to find the mistake and tell me about it in my office gets a prize. How about that? Also, I reserve the right to choose what's a prize. Next question is question 39. Incidentally, there's another way to do this question. I was kind of avoiding it, but instead of these constant acceleration formulas, use the constant acceleration formula 2a delta x is equal to v final squared minus v initial squared. 1e7 minus 1e7 all squared minus 2e5 all squared divided by 2 divided by 0.012. Yeah, you get a different number than this. So that number is wrong. Alright, well, whatever. Let's move on. Question 39. Based on the curve v of t in the diagram, let me repeat the curve of vt. Here's what it looks like. Here's what the diagram looks like. Looks like this. Based on this curve, explain whether each of the statements is necessarily true for the time interval shown in A, such as this, I guess. The acceleration is constant. The acceleration is the slope of this graph, and this graph has a constant slope, so yes, the acceleration is constant. B, the object passes through the position x is equal to 0. It's got to be, it's not necessarily true. So any statement that isn't necessarily true is a false statement. I don't know if you knew that. So in this case, it's not necessarily true because we don't know what this represents, right? Like, we don't know the initial position. It might be that, like, x is equal to 0, and this corresponds to us throwing a ball upwards. In the amount of time shown, it might only be this window, and it still hasn't reached this point because we don't know its initial position. So, too bad. The object has 0 velocity at some instant. It surely does. D, the object is always moving in the same direction. No, I'd say it wasn't. The reason we know it's not moving in the same direction is because over here it's moving in the positive direction, and over here it's moving in the next negative direction. This isn't about slope, it's about the height of the v versus t diagram. Positive height, that means a positive velocity. Negative height, negative velocity, going backwards. Next question, question 40. It says in 1997, Andy Green broke the sound barrier on land in a jet-powered car traveling 763 miles per hour over a 1-mile course. As it arrived at the beginning of the measured mile, Green's car has accelerated to 763 miles per hour over a 5-mile stretch. What's Green's acceleration in that 5 miles? Oh. I guess the implication here is that they're starting from rest. So 5 miles long, start from rest, go faster and faster and faster and faster. And at this point in time, you're going 763 miles per hour. So, how do you do this? Literally the same way as we did the other one. Let's see. In other words, we can either go 2a delta x is equal to v squared final minus v initial squared. So it's 763 squared minus 0 squared 2a times 5. 763 times 763 divided by 10. 508,216.9 miles per hour squared. Alternatively, what we could do is we could do it the long way, the fun way, where you have to start by assigning coordinates. And that's in the positive direction, increasing. So let's go. X0 is 0. V0 is 0. So x is equal to 1/2 acceleration, the amount of time squared. And v is equal to 0 times at. So at t is equal to t finish, I guess start line, v is equal to 763 and x is equal to +5. So 5 is equal to 1/2 a t finish, and 763 is equal to a t finish. So we put them together. How should we do this? Let's solve for t fin. T finish is equal to 763 over a. And then you put this into 5 is equal to 1/2 a 763 over 2 squared, which becomes 763 squared divided by 2 . So that's 291,084 miles per hour divided by a is equal to 5, and rearrange, and that's 58217 miles per hour squared. Hey, look, it's the same. It's because this equation actually comes from algebraically combining the x versus t and v versus t equations. They're the same. Anyway, 40b, calculate the time interval needed to reach its maximum speed. So what's the time interval? T final 763 divided by 58217. 0.0131 hours. Which is 47 seconds. So it almost took a minute of acceleration. But still, guy's spine probably hurt afterwards. Next, it's question 54. 54 goes like this. A rocket ignited on the ground travels vertically upward with an acceleration magnitude 4g. A spent rocket stage detaches from the payload after the rocket has accelerated for 5 seconds. What speed does it hit the ground? That's a fun question. Okay. So, let's talk about its motion. There's two parts to the motion. Let's draw it. Okay, so there's the rocket. This is what rockets look like. Okay. And it accelerates upwards. For how long did it take? 5 seconds? 5 seconds. So then when it's up here, the bottom part and the top part detach. Click. And I guess the top part keeps going on up while the bottom part, well, what does the bottom part do? Let's think about it. At this moment, they both have some velocity, right? So at this moment, the top of the rocket continues traveling upwards with even more velocity, but the bottom part continues to rise on its own velocity. So it goes here, and then it goes upwards a little bit more to a maximum height, and then it falls down back to the ground. So this question seems super complicated, but the whole thing just depends on two issues. Issue one, what's this initial velocity? Issue two, what's this initial height? If we can figure out what the velocity and the initial height are, we're good to go. So we're going to do this in two stages. Before detach, after detach. And we're going to use the answers from this part, from before, to start this question. So before the detachment, the initial position, let's put 0. Alright, I guess I got to draw the reference frame. I'll set this as x equals 0, and I'll put that as increasing. So I'm not a sociopath. V0 is equal to 0, and the acceleration is, it says it's upwards of 4g, so that's 4 times 9.81. Whoa, where'd that come from? 39.2 meters per second squared. Okay. So the position versus time equations will be position is equal to initial velocity 0, initial velocity position 0, and velocity are 0. So this is going to be 1/2 times 39.2 all squared t squared, and v is equal to 39.2 times t. So I'm going to use these at t is equal to 5 seconds. The position and the velocity are nope, 39.2 squared. Wait, 39.2 squared, that's weird. Should be that. Alright. Mistakes were made. 39.2 times 5 times 5 divided by 2. That's 490 meters. And 39.2 times 5, that's 196 meters per second. So now we know how fast it's traveling at this moment. So now the first part of it was this part of the motion. And now we can use these pieces of information to figure out the second part of the motion. We'll call it t prime is equal to 0. That's when we detach. So after you detach, it's just going to fall under its own weight, and so it's going to have the acceleration from gravity. Initial position is 490 meters. Initial velocity is 196 meters per second. Acceleration is minus 9.81 meters per second squared. Position is a function of time. 490 plus 196 t prime minus 9.81 over 2 t prime all squared. V is equal to 196 minus 9.81 times t prime. So now we can use these to answer the questions. What are the questions? Questions are, what speed does the rocket hit the ground? Okay, so again, I don't know what the final velocity is, I do know that it hits the ground. So if I knew what time it hit the ground, I could figure out the position and the velocity. But I don't know. What the thing I do know is that at t ground, x is equal to 0. So I do that. And then I find t prime and I plug it in there. Although there's another way to do this. And the other way to do this is to use that equation I showed you earlier. I don't know why it keeps popping up. I think I accidentally chose a bunch of questions. V final squared minus V initial squared. This equation comes about by taking this equation here and solving it for t and plugging it into this equation here. And you get literally this thing. So my acceleration is minus 9.81. My initial position, or my final position is 0. My initial position is 490. V final is what I want to know, and the initial velocity is 196 squared. So I'm going to solve this. 490 times 9.81 times 2 plus 196 all squared. So that's this raucous beast. And square root answer. So the final velocity is going to be 219 meters per second. Is that the case? Let's check. It's fun to check. So 219 is equal to 196 minus 9.81 times t prime. So let's find out what time it hits. "42 seconds after." And at 42 seconds after, the position is going to be 490. So let's check that the position hits the ground. Okay, 4 meters. That's within the error. We're working with 3 sig figs here, so that's cool. That's close enough to 0, so it works. There's your final answer. Okay, next question is 61. 61 goes like this. Starting from rest, a cart takes 1.25 seconds to slide 1.8 meters down an inclined low friction track. What's the angle? It's tired. That's what the angle is. Okay. So it doesn't take much work to find out that the acceleration down this is going to satisfy g times sine theta down the hill. The data they give us say that the thing starts from the top, from rest, and then it ends up down at the bottom 1.8 meters away. And this is at time 1.25 seconds. So the trick to this, it's another constant acceleration problem. The trick here is that first we need to figure out exactly what the acceleration number is. Oh geez, this thing, it's driving me bonkers today. We need to figure out exactly what the acceleration number is, and then when we do it, we can use this relationship to figure out what the value of theta is. Okay, so we start by assigning a coordinate system, just like every day. So we'll call that x is equal to 0, and we'll make downhill increasing, just for fun. So x0 is equal to 0, and then x bottom is at plus 1.8, and v0 is equal to 0. And the acceleration is unknown. So let's put them into the equations. Position is equal to 1/2 at squared, and velocity is equal to at. Great. We know that a lot of things are 0, and that simplifies these equations, but essentially you look at these and you're like, oh gosh. Yeah, don't lose hope. Always count your numbers of variables. We have 1, 2, 3. Wait, I recounted that. 1, 2, 3, 4 equations, and sorry, 2 equations and 4 unknowns. So we need 2 pieces of information to continue cracking this code. What are these 2 pieces of information? It's this one and this one. So we know that at t bottom, I'll call it TB for fun. So it's at 1.8 is equal to 1/2 a TB squared, and oh, we know the bottom time. We know the bottom time. We know that it's 1.25 all squared. V is equal to a 1.25 all squared. Nope, no squared on that one. All right. So this means that we've got 2 equations and 2 unknowns, and they're not very hard to solve. I'm going to solve this one for the acceleration. .304 meters per second squared, and so we can plug it into this equation to find theta. A is equal to 2.03, nope. Okay, so arcsine answer, theta is 13.5 degrees. Huh. There's another way to do it that's also kind of fun. If you, let's see, instead of using inverse trig, one thing you can do is, if you know how much time it took and you know the acceleration, you can calculate the final speed. And then if you know how to do these things, you can essentially say, oh, if I know this final speed, I can figure out what the initial gravitational potential energy is. And if I know the initial gravitational potential energy, that tells me this side. And so I know this side of the triangle and this side of the triangle, and I just find this one using trig functions. But we don't know how to do that yet in class, so don't worry about that. Okay, so I'm going to pause the feed. Oh, hold on. 60, 61, we can do 75 still. Okay, so one more and then I'll do the feed pause. 1 or 2 more. 75. A particle is accelerated such that its position as a function of time is given by... So this is 1. B is equal to 1. T cubed, I hat. We want the acceleration as a function of time. How do we figure that out? Derivatives. So the velocity is the time derivative of the position vector. So I'm going to use the power rule. And the power rule says that this is equal to 1 times 3 t to the 2. Where's that 1 come from? Comes from over here. I hat. And the acceleration is the time derivative of the velocity. Jeez. So this is 3t squared, I hat. And so its time derivative is 3 times 2t to the 1, I hat. So it's 6t, I hat. Done. Okay. 75. I guess the next one is 85. 85. Question 85. It takes you 7 meters to brake to a panic stop from a speed of 9 meters per second. Using the same acceleration, how far do you go if you brake at a panic stop from a speed of 27 meters per second? Okay, so in other words, you have some initial velocity that's 9 meters per second, and you hit the brakes, and that's going to take you a certain amount of time to stop. Takes you that distance. They give us this distance, which is 7 meters. And the implication here, you can calculate the constant acceleration vector required to do that. And then the second part of the question goes, okay, suppose I'm traveling much faster. What is this one now? 27 meters per second? I'm going to apply the same acceleration, and that's going to cause me to slow down. It's going to take me much farther and more time to slow down to a stop, and that'll give me this distance. So I want to compare these two distances. How do I do it? Well, first I have to calculate the acceleration. So how do you calculate the acceleration of this one? You can use the thing where you define the position as a function of time and then do algebra, but I'm just going to skip to this. No. It's important to get your equations right when you use them. X final minus x initial is equal to v final squared minus v initial squared. So the deal here is this 2 stays the same, a. The change in position is 7. Your final velocity is 0, and your initial velocity is 9 squared. So you do your calculation. 9 times 9 divided by 7 divided by 2. So it's minus 5.78 meters per second squared. So we want to know what this distance is, right? So we can essentially use the same equation. 2a delta x is equal to v final squared minus v initial squared. So this is 2 times minus 5.78 times delta x is equal to the final velocity is 0. The initial velocity is 27 squared. So you rearrange this and you get 63.0 meters. All right, now it's time for me to stop my feed because there's a weird bug in this. Oh, it's already happened. Oh, and nobody said anything. Okay. There's a bug with the software I'm using. I'm kind of using a kludge, sticking different solutions together. So part of this problem means that I have to regularly set and unset this thing. About once an hour it'll conk out. Okay, well the hour's over, so I fixed it, so we should be good for another hour. This is what we missed. So all I was saying here is that your initial velocity is big, and then it slows down to a stop. There's that motion diagram. And so we're given the initial velocity and the distance it takes. And then the second part of the question, we're saying, what if this acceleration is the same? The initial velocity is much bigger, so it's going to take a longer amount of distance to come to a stop. Let's figure out what that value is. I use this warhorse, which has served me well all thing to use. I think this is in your textbook. You know, last class we derived it in class, and this year I didn't, because I don't know why I didn't. But long story short, this is a constant acceleration equation, relationship between the displacement and this change in speed. So I just plug these numbers into this guy. Distance, displacement, final velocity, initial velocity, calculate it down, calculate the area, and I'm going to use it again for this problem. I know its acceleration, I don't know its displacement, but I know its final velocity 0, and I know its initial velocity, and you can then just crunch the numbers and get your answer. Okay. Let's see if anybody has any problems with it on the thing. Nobody says they have any problems. Nobody says anything. Okay, time to move on to the chapter 10 questions. Turn your page to page 181 in your black book. And, oh, hey, I decided to do 4 questions. Ugh. All right, so first question is going to be question 39. Which is the best representation? Okay, so there's a diagram. The first one goes like this. That's called A. And the second one goes like this. It's called B. And the third one goes like this. It's called C. Which is the best representation of a cantaloupe thrown horizontally off a bridge? What's wrong with the other paths? Geez. Which one's the best? Of all of them, I think... So your motion is going to be parabolic. It's going to be shaped like a parabola. So I think that this is the right answer, because this was the one that looks most like a parabola. This one kind of looks like a parabola. This one definitely doesn't look like a parabola. So why doesn't it work? One way to think about this is that you want to break it in. You know that the horizontal... Oh, jeez. You know this software... It's an app I paid for, but it doesn't... It's being janky today. Because of how it moves, it's going to move in one time unit. It's going to move the same horizontal distance in each of them, because it's horizontal motion. So horizontal distance, horizontal distance. So then when you've broken it up like this, you can then ask yourself things like, hey, how's the y velocity, y component of the velocity changing? So, you know, for instance, this one, the y component of the velocity starts very small, and it continues being very small until around here, where it gets really big. And you would expect the y velocity to increase by regular increments. So here the velocity starts out small, and then it gets bigger, 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 and then it looks kind of okay. Here it starts out small, it gets bigger, bigger, bigger. Yeah. So I'm not sure. B and A both look pretty good, at least artistically. I think B has too much curve like that to it, but you know, there's art. It might be that A is a little bit too flat on the end. I'm not quite sure which one they're going for, but my guess is A. Next question, 41. A rifle is aimed horizontally at a target 100 meters away. Hasta la vista, baby. So that's the target. And it says that the bullet goes... If this doesn't stop being bad, I am going to switch programs. It has one more strike. 650 meters per second. So it doesn't hit the bullseye. Good news. The bullet won't go straight across horizontally because the bullet's going to follow a projectile motion path and go down here. So the question is, what's that distance? How do we start this problem? That's the question we're all asking. And the answer is, well, you break it into components. So you're like, what's the velocity? V vector. The initial velocity in the x direction is 650 meters per second. The initial velocity in the y direction is 0. And then we need a reference frame. We probably needed one to assign positive to the right. So let me call this original position, I'll call that the origin, and I'll call going up positive and going to the right positive, increasing. Okay, so that's an increasing vector. So let's continue on our journey. Our initial position is 0, our initial y position is 0, and our acceleration in the x direction is 0, and our acceleration in the y direction is minus 9.81 meters per second squared. So now let's put it all together. Vy is equal to 0. Okay, you know what? I'll write it all out, and then I'm going to erase it just because. 9.81 times t. Vx is equal to 650 plus 0 times t. Y is equal to 0 plus 0t minus 9.81 over 2t squared. And x is going to be, come on, look at that. Cripes on crops. Stop being so buggy. Right, initial position 0. The initial velocity is 650 times t, and the acceleration is, look at that, make you weep. 0 over 2 t squared. Now, I'm going to erase all the 0 terms just so that I have something nice to look at. Okay. So this is actually a lovely beast. There's 4 equations, all of them involving t. And so the question here is, where does it hit the wall? How far below the target? And so to answer that, if I knew what the t was when it hits the wall, I would be all set. So to figure that out, we know that the wall happens at x is equal to plus 100. So that's equal to 650 t. So t wall is equal to, get out calculon, 100 divided by 650, nope, there, 0.154 seconds to 3 sig figs. And then I plug this into y. I want to know when y wall isn't the right thing, but I want to know the y coordinate when it hits the wall. So I do. 0.154 times 0.154 times 9.81 divided by 2 minus 0.116 meters. So it's 11 centimeters too low. Almost 12 centimeters. 11.6 centimeters too low. Which is pretty low. Okay, let's go to the next question. 50. Question 50 goes, how far does a fastball released from the pitcher's hand at a speed of 42 meters per second fall as it travels from the pitcher to the batter a distance of 18.4 meters? Your answer gives you a good idea of why the pitcher stands on a mound of dirt. This question is literally the same as the previous one. The previous one, oh, they're both 2-star. Okay. Well, let's do it. So here's your pitcher. Okay, and then oh no! You know what? I was trying to draw a pitcher, but instead I accidentally drew a belly itcher. Oh, jeez. Sorry, everybody. 42 meters per second. Okay, so just like in the previous one, this is going to drop. I don't know how far. But, or rather, the place I'm interested in is a location which is 18.4 meters away. Okay. So to tackle this question, I start by assigning an origin. Where do you want the origin to be? How about where the ball gets released? Okay, so this location is at x is equal to plus 18.4. I'll say this way is increasing and this way is increasing. Okay. So let's start filling out the things we know. The initial position is 0. The initial height is 0. The initial velocity in the x direction is 42 meters per second. The initial velocity in the y direction is 0. The acceleration in the x direction is 0. The acceleration in the y direction is minus 9.81. So we plug all these into formulas. X is equal to 0, 42 times t, y is equal to 0, minus 9.81, divided by 2t squared. Vx is equal to 42. Vy is equal to minus 9.81 times t. Okay, so we want t at the batter. And that's when, oh geez. So I want to figure out the time when it reaches 18.4. So t at that time, oh geez. I'm at the end of my rope with this. I wonder if it's because the screen is all crappy. Hold on, buckle up. I'm gonna try dusting the screen. Okay. I thought that would be wigglier than it was. Right. So I want to calculate the time it reaches the end. 42.42, 0.438 seconds, and so y at that time is 0.4. Come on. Guess it wasn't that. 4.438 all squared. Oh god, this is terrible. I am actually smudgier with the stylus than I am on my normal screen. With pen. Oh, for cripe's sake. This thing, it's being so bad. So it's going to be 0.9. Not 0.940 0.94 meters. That's the answer. So there you go. That's how far. And so the if you put the pitcher on a 1 meter high mound, then by the time it gets to the batter, it will be batting height on the batter. Choke up on that bat, mister. Jeez, I'm sorry everybody. Y'all wanted me to draw a batter, but instead I drew this broken ladder. Well, as long as I have fun. Also, is the thing updating? Oh, the stream. Okay, well, it's doing its best. You can do it, stream. Alright, you know what? Let's switch programs. Maybe the notes program will work better. Notes. Give me a note. Alright. So that was question 50, right? Yeah, last question. Question 52. So 52 goes, a burglar evading police is running as fast as he can on a building's flat rooftop. At the edge, he sees another flat rooftop across an alley. The horizontal distance across the alley is 8 meters, and the other rooftop is 3 meters lower than the one on which the burglar is standing. He can run the 50-meter dash in 5.6 seconds. Can he make the leap when moving at full speed? You know what? There's the way they want us to answer the question, and then the way that I am tempted to answer the question. So you always start with the drawing, right? So here you go. Here's Daredevil with his stupid Daredevil horns and his cool body armor, and he's running and doing parkour so fast. And then you want him to jump over the thing. So, the parameters of this are that this distance here is 8 meters, and that this drop here is 3 meters. So, let's see, what's the best way to do this? The issue with this question is there's actually a lot going on. So here's the dude. What's his initial velocity? Are they assuming that the initial velocity is horizontal? And regardless, is he going to make it across? That's the question. So the easiest way to do this is to just, go, oh, well, let's just assume they're moving horizontally. This one doesn't do that thing. Let's just assume they're asking for horizontal motion and go from there. Well, that's lovely. How do a pen? Does this pen work? Oh, gross. Oh, what? Holy crow. Look at this, you guys. This is bonkers. It's in inches, though. Jeez. I wonder if there's a setting that can let me change this to centimeters. Anyway. Okay. So let's assume horizontal velocity. Okay, if that's the case, actually, before I go anything, I need to calculate his maximum speed. So the thing says that he can run the 50-meter dash in 5 seconds. Let's assume he's running at constant velocity during the 50-meter dash. So then it's 50 meters divided by 5.6 seconds. So that's 8.92 meters per second. Oh, right, coordinate system, hold on. So I'll center it like that, and I'll make that increasing, and I'll make that increasing. Okay. So, what's to be done now? V0x is 8.92 meters per second. V0y, oh no. What if it's something wrong with my pen? I don't think so. Let me try redocking my pen. This is ridiculous. Also, this isn't a problem that's happened in the previous... Get in there. Alright. This isn't a problem that's happened before in my previous attempts to use the stylus, so I'm not quite sure what's going on. Whoa, hold on. Hold on. Okay. X0 is equal to 0. Y0 is equal to 0. AX is equal to 0. AY is equal to minus 9.81. Oof. So let's put these into equations. X is equal to 0, 8.92 times t. Y is equal to 0, 0. Jeez. T squared. Oh no. Oh, you know what? I think it's the hand recognition isn't going so good right now. Oh, there's other colors. Good for us. Vx is equal to 8.92. Vy is equal to minus 9.81 times t. All right, so I need to know what time it reaches x is equal to 8 meters. So I'm going to use this equation here. Oh god, that's terrible. I'm going to use this equation here. I'm going to use this equation here. Gross. All right, so that's 8 divided by 8.92. So that's going to be at t is equal to 0.896 seconds. And then y at that time is minus 9.81 times 0.896 all squared divided by 2. Minus 3.93 meters. Okay, so that's not very good. There's a possibility, though, that you jump. And this one doesn't assume that you jump. This calculation we've done doesn't assume that there's been any jumping at all. So let's... Actually, that's not the only problem. Another problem is that we've assumed that the person's traveling, doing the 50-meter dash at constant velocity. What if the 50-meter dash starts with v initial is equal to 0? If that was the case, then there would be an acceleration. I don't know what the acceleration is, but I do know that in delta x is equal to 50, the time would be equal to 5.6 seconds. So 1/2 a times 5.6 all squared. To run that from a stop, your acceleration would have to be 50 times 2 divided by 5.6 divided by 5.6, 3.18 meters per second squared, assuming uniform acceleration. And that would mean that its final velocity, you can calculate that using 2a delta x vf squared minus v initial squared. Your initial velocity is 0, vf squared, so that's 2 times 3.18 times 50. 2 times 3.18 times 50, square root it. V is equal to 17.8 meters per second. So if you ran the 50-meter dash in this much time from a stop, this is his final velocity. And you need to understand something about this velocity. It's faster than Usain Bolt. It's quite a bit faster than Usain Bolt. Usain Bolt runs the 100 meters in a little under 10 seconds. So that means that his velocity, his max speed, is something like... Well, he's doing a constant acceleration too, to be quite honest. But this is still quite fast. Nevertheless, let's see if our burglar now makes it with this ridiculous speed. So this is now 17.8 meters per second. And that makes this one 17.8. Or whatever that. X is equal to 17.8 times t, 17.8. So at what time does he reach 8 meters? Whoa, what's that thing again? That's the very worst. That's going to happen at... No, wait, hold on. I want... When x is at 8 meters, I want to figure out what t is. So 8 divided by 17.8, 45 seconds, and then your y velocity is equal to your y position is minus 9.81 divided by 2 times 0.45 times 0.45. 0.99 meters minus. So if this information is based on an inaccurate assumption and the person is actually accelerating from stop, they will make it in time. Their trajectory will be like, whoa, and they'll end up 2 meters above the roof, which is a hell of a distance to fall, to be quite honest. It's like falling over 6 feet, but whatever. They can run faster than Usain Bolt. They have other problems. Okay, so another way of addressing this problem. So that was just one of the possible misassumptions that they weren't quite clear about. Like I said, all of this stuff here, undo all of this stuff we just did here. That's weird. That final velocity is weird. I think they intended that we do it this way. So another misassumption might be that the person actually has an initial velocity. So they jumped, or maybe ran over a ramp, taking them into the air. So the question is, what's a good initial velocity? Well, what angle should we use? How about if we use a 45-degree angle? Because that usually, if you're just throwing a football across a field, a 45-degree angle will make it go furthest over a flat field. If we do that, then your initial velocities are going to be different. Velocity in the x direction is going to be 8.92 times cosine 45. So this number is going to now be 6.3 meters per second, and this number is going to be 6.3 meters per second, both in the positive direction. This changes some of these equations around a little bit. The position is a function of time. Equation is going to be 0 plus 6.3 times t, and the y1 will be plus 6.3 times t minus 9.81 over 2t squared. 6.3 minus 9.81 over 2. Nope, over 2. T squared. Are these numbers the same? It's because cosine 45 and sine 45 give you the same number. Okay, so now what? Now I have to crack the problem again. At what time do you reach 8 meters? In this case, you'll reach 8 meters in 8 divided by 6.3, 1.2. Oh, geez, that thing happened again. No, erase. Okay. At 1. 1.3 seconds. It's 1.27 seconds, but whatever. So the y position at that time is 6.3 times 1.3 minus 9.81 times 1.3 times 1.3 divided by 2. All right, so if you jump at a 45-degree angle, you're going to end up almost at the same height you left, to be honest. And so you'll make it safely. So the question, I'm not quite sure what kind of answer they were looking for. The question is, can he make a leap when moving at full speed? And the question is, well, what do we mean by full speed? If full speed means the data you gave us is a constant velocity, then, and he jumps horizontally, then the answer is no. But if the data you gave us indicates that he can move vertically, all right, sorry, if the data you give us indicates starting from a stop in the 50-meter dash, then it's possible with a horizontal jump you can make it. And if instead of running horizontally he jumps up in the air, he can definitely make it. Anyway, that's the end of the thingy. I hope you had fun. I'm not sure I did. This stylus is driving me bonkers. But have a nice day. All right, let's stop streaming.